For decades, we thought we understood the outer solar system. We believed we had categorized the planets neatly. Rocky worlds close to the Sun, gas giants like Jupiter and Saturn, and then, far beyond, two frozen, distant worlds we confidently labeled ice giants. One of them was always the quiet one, the tilted one, the strange one, and that world is Uranus. Discovered in 1781 by William Herschel, Uranus immediately broke the rules. It didn't behave like the other planets. It rotates on its side, tilted at an extreme 98 degrees, as if some cosmic catastrophe knocked it over. Instead of spinning upright like Earth or Mars, Uranus rolls around the Sun like a giant icy barrel. For half of its 84-year orbit, one pole faces the Sun in continuous daylight while the other is locked in darkness. If you think Earth's seasons are dramatic, Uranus redefines the concept entirely. But the real mystery wasn't just its tilt. Scientists classified Uranus as an ice giant because of what they believed filled its interior: water, ammonia, and methane ices compressed under immense pressure. Unlike Jupiter and Saturn, which are dominated by hydrogen and helium gas, Uranus was thought to contain a much higher percentage of these heavier, icy, materials. That classification stuck. It was repeated in textbooks, documentaries, and classrooms for decades. Yet something never quite added up. In 1986, NASA's Voyager 2 spacecraft flew past Uranus, giving humanity its first, and so far only, close look at the planet. What it saw was underwhelming. Compared to the swirling chaos of Jupiter's storms or Saturn's rings, Uranus appeared almost blank. A pale blue sphere with barely visible cloud bands. Calm, quiet, almost boring, but science doesn't judge by appearances. Voyager 2's data revealed something puzzling. Uranus gives off almost no excess heat. This is incredibly strange. Every other giant planet radiates more heat than it receives from the Sun. Jupiter glows with leftover heat from its formation. Saturn does the same. Even Neptune, farther from the Sun than Uranus, radiates significantly more internal heat. Why doesn't Uranus? That question has haunted planetary scientists for decades. If Uranus formed the same way as Neptune, why does it behave so differently? If both are ice giants, why does one radiate heat and the other seem almost thermally dead? Why does Uranus have such a strangely weak internal energy signature? Why does its magnetic field tilt wildly off-center? Why does its atmosphere appear more subdued than expected? The deeper scientists looked, the more the ice giant label began to feel simplistic. Because classification is easy, understanding is not. As telescope technology improved, researchers began modeling Uranus's interior in greater detail. Instead of a simple layered structure, atmosphere, icy mantle, rocky core, the data began suggesting something more complex. Some models indicated that the planet's interior might not be dominated by ice in the traditional sense at all. Under extreme pressures, water and ammonia do not behave like the ice we know. They transform into exotic states of matter, superionic water, where oxygen atoms form a crystalline lattice while hydrogen ions flow freely like electricity. This isn't frozen slush. This is alien physics. And that changes everything. Because if the internal structure of Uranus is far more dynamic and exotic than originally believed, then maybe calling it an ice giant is misleading. Maybe it's something else entirely. Maybe we've misunderstood its composition from the start. And here's where things become even more intriguing. Recent simulations suggest that instead of having a well-defined rocky core surrounded by thick icy layers, Uranus might have a more diffuse interior, materials mixed together in gradients rather than separated into neat layers. If true, that would challenge traditional planetary formation models. It would suggest that Uranus experienced a violent collision early in its history, one powerful enough not only to tilt the planet sideways but to scramble its internal structure. That impact theory isn't new, but the consequences of it might be far greater than we imagined. What if Uranus isn't a standard ice giant at all? What if it's a planetary hybrid, something between a gas giant and an ice giant? What if the name itself is wrong? Because when science advances, certainty disappears. And Uranus may be about to rewrite its own story. For years, Uranus was the forgotten planet. It received little attention compared to Mars, Jupiter, or Saturn. But modern telescopes have changed that. Infrared observations and advanced atmospheric modeling have revealed details Voyager 2 could never capture. And what scientists are seeing doesn't fully align with the ice giant narrative. First, let's compare Uranus to Neptune. Both are similar in size, mass, and distance from the Sun. Both are blue due to methane absorbing red light. Both were labeled ice giants. But Neptune is active. Violent storms rage across its atmosphere. It radiates internal heat strongly. Its winds are the fastest in the solar system. Uranus, much calmer, much colder internally, almost eerily quiet. That difference suggests something fundamental is different beneath the surface. Some recent models propose that Uranus may have a thinner, icy mantle than previously thought. Instead of thick layers of frozen volatiles, much of the interior could consist of hot, dense fluid mixtures behaving more like supercritical fluids than solid ice. Under extreme pressure, water doesn't freeze in the traditional sense, it becomes electrically conductive and dynamic. This could explain Uranus's strange magnetic field. Unlike Earth's magnetic field, which is centered and relatively stable, Uranus's magnetic field is wildly tilted, nearly 60 degrees from its rotational axis, and significantly offset from the planet's center. It's chaotic and asymmetrical. Why? If the magnetic field is generated not deep in a solid core but in a shallow, convecting layer of superionic water and ammonia, that offset suddenly makes sense. The dynamo effect might be happening in a strange shell rather than a central core. In other words, Uranus might not have the kind of internal layering we expect at all. There's more. Thermal evolution models suggest that if Uranus experienced a massive collision early in its formation, that impact could have expelled much of its internal heat into space. It could have disrupted convection currents inside the planet, effectively locking in its cold interior. That would explain why it radiates so little heat compared to Neptune. But if such a collision mixed its interior materials thoroughly, the result wouldn't be a classic ice giant. It would be a chaotic, blended world with a unique composition and structure. And here's where exoplanets enter the picture. Across the galaxy, astronomers have discovered thousands of planets. Many of the most common types are similar in size to Uranus and Neptune. These so-called sub-Neptunes are abundant. But we don't fully understand them, because we don't fully understand our own ice giants. If Uranus is misclassified, then our entire interpretation of these distant exoplanets might also be flawed. That's huge. It means Uranus isn't just a distant curiosity. It's a key to understanding planetary formation across the universe. And we may have been oversimplifying it all along. Science evolves by questioning assumptions. The term, ice giant, was useful. It separated Uranus and Neptune from the massive gas giants. But new research suggests the distinction may not be so clean. Instead of neat categories, rocky, gas, ice, planetary interiors might exist on a spectrum. Uranus could represent a transitional world, not dominated by thick frozen ices, not purely gaseous, but composed of exotic high-pressure fluids, superionic layers, and partially mixed materials that defy traditional classification. It may not be an ice giant in the way we imagined. And that changes how we see it. Future missions are already being discussed. A dedicated Uranus orbiter could map its gravitational field in detail, probe its atmosphere, and measure its magnetic anomalies precisely. Such a mission could reveal whether the planet's core is compact or diffuse, whether its internal layers are distinct or blended, and whether its ice behaves more like a strange ocean of electrically charged fluid than frozen matter. If those missions confirm what models are hinting at, textbooks will change. The quiet blue planet rolling on its side may turn out to be one of the most complex and misunderstood worlds in the solar system. Sometimes the biggest discoveries aren't explosive. They're subtle shifts in understanding, a reclassification, a new model, a realization that nature refuses to fit into human-made categories. Uranus might not be an ice giant after all. It might be something far more extraordinary, a planetary experiment in extreme physics, a hybrid world shaped by violence, pressure, and time. And if that's true, then the story of our solar system just became far more interesting. Because the farther we look into space, the more we realize we are still beginners, and the universe is still surprising us.